We're going to now derive the impedance of an inductor. You'll recall that we have defined the impedance as being the ratio of the phasor voltage to the phasor current. So let's now derive that relationship, phasor voltage to phasor current, for an inductor. Here we have an inductor, and we'll reference the voltage V of t, plus to minus like that, and also reference the current through it, I of t, where the current is referenced from the high voltage, referenced in the direction of flowing from high to low voltage. Now, let's just assume that I of t is of the form I sub m cosine of omega t plus theta sub I. So the current we're assuming is oscillating at the same frequency as the source that's driving the circuit. It has an amplitude I sub m and a phase angle associated with it of theta sub I. Now we know that in an inductor, the voltage across an inductor is proportional not to the current, but rather proportional to the derivative of the current, or V is equal to L times di dt. So we've got then L. Now di dt, we're going to have I sub m, and the derivative of the cosine is negative sine, so let's bring the minus sign out here in front. And let's also go ahead and we're going to have the chain rule invoked here, so let's bring the omega out in front associated with a chain rule. And then we will have the sine of omega t plus theta sub I. Now ultimately we're going to want to have this, or represent V in terms of its phasor, and so we need to convert the sine term to a cosine term. So this then is equal to negative L I sub m omega times the cosine of omega t plus theta sub I minus 90 degrees. Shifting the sine wave 90 degrees to the right gives us a cosine wave. Now we can write I sub m in terms of its phasor, or phasor I is equal to I sub m e to the j theta sub I. And phasor V will be equal to, we've got the negative sign, the Li omega is its amplitude, so negative L omega I sub m, and then it'll be e to the j theta sub I minus 90 degrees. Now, using the property of the product of exponents, let's rewrite this then as equaling, let's see, negative L omega I sub m e to the j theta sub I e to the j, let's see, negative j 90. Now, let's look at this term e to the minus j 90. Just drawing a little phasor diagram over here. E to the minus j 90 has a magnitude of 1, and it has an angle of minus 90. That's equivalent to, this e to the minus j 90 then is in the negative j direction with a length of 1, or we can rewrite this term right here as a minus j. Now, let's combine this minus sign here with this minus sign here, bring the j here into this, bring the j into the mix here, and we get then that phasor V is equal to, minus times minus is a positive, and we'll have a j omega L e to the j theta sub I. Oh, and I left an I sub m term multiplying all of that also. Now, we notice that right there is I sub m e to the j theta sub I. Well, that's just phasor I. And we have then that phasor V is equal to j omega L times phasor I. Phasor V, Z is defined as the ratio of phasor V to phasor I, which is equal to then, phasor V is j omega L times phasor I divided by phasor I. The phasor I's cancel, And we're left with the impedance of the inductor is equal to j omega L. Let's just look at this for a second. In other words, the impedance of an inductor is equal to j times omega times L. Note two things. First of all, the impedance is imaginary. It's j. It's also positive. The second thing we'd like to point out is that it is a function of frequency. Here, the frequency of the source that's driving the circuit determines or impacts or it is involved in the impedance. The impedance is related to the frequency. In other words, as the frequency gets larger and larger, the impedance gets larger and larger. Or as the frequency gets smaller, the impedance gets smaller. And in fact, in the limits, when omega equals 0, the impedance of the inductor is 0. The ratio of the voltage to the current is 0. In other words, at DC, there is no voltage drop across the inductor. But we knew that. At DC, di dt is equal to 0, and the voltage across the inductor is 0. Now, as omega goes to infinity, the impedance of the inductor becomes infinite, or it would be equivalent to an open circuit. In other words, at high frequencies, the voltage across here, the derivative of the current goes to infinity, and the voltage across it goes to infinity. There is no, it's an open circuit at that point. Nothing gets through it. Let's just take an example. Let's assume that we have a source, V of t is equal to 5 cosine of 100 t. In other words, omega is equal to 100. And let's say we've got a 50 millihenry inductor. Let's let L equal 0.05 Henry. Then the impedance of that inductor, Z sub L, will equal J times omega, which is 100, times the inductance, which is 0.05, and we get that the impedance of that inductor in a circuit oscillating 100 radians per second is equal to J 5 ohms.